So I can share my screen, right?
Yes, visible.
Okay.
Yes, visible.
Okay, I am ready.
Okay. Thank you. Yeah, it's perfectly visible. Moutushi madam, we can start now.
Okay, sir. Okay, sir. Okay, sir.
You can start, yeah.
Okay, sir. So good morning, all the delegates. I, Dr. Moutushi Singh from Institute of Engineering and Management, Kolkata, wholeheartedly welcome you all today in this online platform for this 3-day-long international conference on network security and blockchain technology, that is ICNSBT 2021, organized by Computer Society of India, Kolkata, from 2nd December to 4th December 2021. The Computer Society of India has been instrumental in guiding the Indian IT industry since its formative years. The mission of CSI is to facilitate research, knowledge sharing, learning, and career enhancement for all categories of IT professionals, while simultaneously inspiring and nurturing new entrants into the industry and helping them to integrate into the IT community. Encouraged by the earlier responses and maintaining its earlier tradition, CSI Kolkata chapter is organizing an international conference on network security and blockchain technology. And today is the 2nd day of this conference. The track of the first session of today is network security, privacy, and its applications. And I'm very delighted to announce that now we are having with us Professor Yingjiu Lee from Oregon University, USA, who is the first keynote speaker of today's session. And he will be discussing on accountable blockchain rewriting. Before he starts, let me introduce him. Professor Lee is currently a Ripple Professor in the Department of Computer and Information Science at the University of Oregon. His research interests include IoT security and privacy, mobile and system security, applied cryptography and cloud security, and data application security with privacy. He has published over 150 technical papers in international conferences and journals and served in the program committees for over 80 international conferences and workshops, including top-tier cybersecurity conferences. We are also happy to announce that today with him, we are having Professor Debashish De, Professor, Department of Computer Science and Engineering, and the Director of School of Computational Science of Makaut, West Bengal, India. He received the MTech from the University of Calcutta in 2002 and a PhD from Jadavpur University in 2005. He is the senior member of IEEE, fellow of IETE, life member of CSI. He was awarded the prestigious Boy Scouts Fellowship by the Department of Science and Technology, Government of India, to work at the Heriot-Watt University, Scotland, UK. He received the Endeavour Fellowship Award from 2008 to 2009 by DST Australia to work at the University of Western Australia. He received the Young Scientist Award both in 2005 at New Delhi and in 2011 in Istanbul, Turkey, from the International Union of Radio Science, Belgium. In 2016, he received the J.C. Bose Research Award by IETE, New Delhi. In 2019, he received the Shikha Ratna Award by the Government of West Bengal. He established the Center of Mobile Cloud Computing, CMCC, for IoT applications. He is the Vice Chair of Due Computing, STC, of IEEE Computer Society. He published in 320 journals and 200 conference papers, 15 books, and filed 10 patents. His research interests are Edge AI, IoT, and quantum computing. Thank you, sir. Now over to you, Professor Lee. We are eager to listen from you, sir.
Welcome, Professor Lee.
Thank you very much for your introduction and also for giving me this opportunity to talk about the recent advancement in research on blockchain rewriting, accountable blockchain rewriting. 12 years ago, I attended International Conference on Information System Security in Kolkata, which was hosted by the Indian Statistical Institute. I still remember my PhD supervisor, Professor Sushil Jajodia, introduced me to some of his friends at Indian Statistical Institute. I wish I could visit Kolkata again, but apparently it is not a good time to travel now. Fortunately, we can still meet virtually and exchange our ideas on network security and blockchain technology. So since Satoshi Nakamoto published the seminal paper, Bitcoin, a peer-to-peer electronic cash system in 2008, blockchain technologies have attracted extensive attention in the last decade and driven continuous development of many large-scale and blockchain-based applications, including digital currency, decentralized finance, supply chain, insurance, energy, and a medical system. In a nutshell, blockchain is an immutable append-only ledger whose state is agreed upon via decentralized consensus protocol. The immutability of a blockchain is essential to prevent anyone from manipulating the registered objects for illegitimate benefits. If anyone makes a change to an existent block, inevitably it will change the hash value of this block and the hash value of each following block. It is impossible to ensure that all the changed block hash values remain qualified under the standard hash function unless the modifier controls a majority of the hash power over the entire blockchain. So while blockchain immutability remains a desired property, it also triggers a serious concern because illicit data contents and the improper data contents have been injected into the blockchain. Such illicit and improper data contents include child pornography, copyrighted material, and other sensitive information. Mozart and others conducted a quantitative analysis of the impact of arbitrary blockchain content on Bitcoin in 2018. They discovered that several low-level data insertion methods can be exploited by attackers to insert arbitrary content in blockchain. Attackers may make use of the op return field in blockchain transaction to insert arbitrary content. Attacker may make use of the input script of Coinbase transactions, the input and output scripts of various standard financial transactions to insert data into blockchain. They also discovered that high-level content insertion services can be built on top of the low-level data insertion methods to add files such as documents or images to the blockchain. Quantitative analysis show that about 1.4% of 251 million transactions in Bitcoin blockchain actually carry arbitrary data content, including 1,600 files. While a majority of such data are harmless, different categories of objectionable content have been identified, including links to illegal pornography and serious privacy violations. So blockchain immutability has become an obstacle that limits the development of blockchain due to the abuse of blockchain storage and illegal obligations. On the one hand, users are unwilling to participate in and download such blockchain because they are afraid of being persecuted for the possession of such illegal information. On the other hand, blockchain immutability is no longer legal since data regulations such as the General Data Protection Regulation, GDPR, grants individual users the right to ask for deleting their personal data, including those in blockchain. To address these concerns and to break blockchain immutability in a controlled way, Antonis and others introduced the concept of redactable blockchain that allows a single trusted authority called modifier to rewrite a registered object without breaking the link between blocks. Blockchain rewriting is performed at the block level. The modifier may rewrite one or more blocks, compress any number of blocks into a smaller number of blocks, and insert one or more blocks. The basic idea is to add a block to each, add a lock to each link of a hash chain using an enhanced community hash. Here, the community hash is this function G in this figure. Without the lock key, it is hard to find the collisions and the chain remains immutable. But given the lock key, it is not difficult to find the collisions and just replace the content of any block in the chain. In this figure, we see that the previous the hash of the previous block S prime is included in the current block here, and then the current block, the hash of the current block is generated from the standard hash function H and the chameleon hash function G. Traditional chameleon hash function proposed by Crosscheck and Robin in 2000, it is not strong against the collision, because collisions must be kept private, since the secret key of the chameleon hash can be extracted from a single collision. The chameleon hash function used for this reductible blockchain is collision, has a property called enhanced collision resistance. It is safe to reveal any number of collisions without revealing the trapdoor. This kind of chameleon hash function can be built from traditional chameleon hash function, public key encryption, and non-interactive zero knowledge. In this figure, G is this kind of a chameleon hash function with enhanced collision resistance. If a modifier rewrite the current block X prime here, this X prime is the root hash of the Merkle hash tree, covering all the transactions included in this block. Okay, if the modifier modifies this current block, the modifier can find out a collision so that this chameleon hash value G remains unchanged. Okay, so even if a modifier changes its X prime, the modifier can find the collision R prime so that this chameleon hash value remains unchanged. And the modifier does not need to change these nonce CTR prime, and the modifier does not need to change this hash value of the current block. If the modifier delete the previous block S prime, or insert a new previous block S prime, so this modifier needs to change this S prime here included in this current block. The modifier can find out a collision here in this chameleon hash function, so that even if this S prime is changed, the modifier can find a collision for R prime so that this chameleon hash value remains unchanged. Therefore, the link between the blocks are preserved in the blockchain rewriting process. After rewriting blockchain with a secret key, the central authority should broadcast the new redacted chain as a special chain, meaning that every user of the system should adopt the new redacted chain in favor of any other chain, even longer ones. This solution has been adopted by Accenture recently in building its blockchain for financial services. Accenture is a leading independent technology organization. They integrate alliances, partnerships, and leaders from every aspect of the blockchain ecosystem. Considering that the previous solution requires a central authority called modifier to rewrite blockchain content at the block level, which is a coarse-grained. Diller and others promoted to shift the focus to fine-grained blockchain rewriting at the transaction level in a decentralized setting. The motivation is that the person who introduces a transaction into the blockchain should be able to determine who will be able to modify the transaction if required. So what to rewrite is shifted from block level rewriting to transaction level rewriting, and who can rewrite is shifted from a central authority to anyone qualified, specified by a transaction owner. In a decentralized setting, every entity, every user can play the role of an attribute authority. They can assign attributes to other users and issue rewriting credential, that is attribute keys to the other users. Then the transaction owner can tag a mutable transaction with attribute-based policy corresponding to attribute authority. Then any user whose rewriting credential satisfies the policy associated with a mutable transaction can rewrite that transaction. One building block for such fine-grained controlled blockchain rewriting is called CHET, the communion hash with ephemeral trapdoor, which was published by Kamenish and others in PKC 2017. The CHET consists of the following functions. First, the public parameter generator function generates public parameter given input of security parameter K. Then the key generation takes the public parameter as input, generates a pair of a secret key and the public key. Hashing a message involves the public key. The hash result includes the hash value, the accompanied randomness R, and an ephemeral trapdoor, ETD. Then this ETD must be used to find out the collision. Okay. So the collision, anyone knowing this secret key of this CHET and the ephemeral trapdoor for a particular hash value can find out the collision for that hash value. So given the hash value H, accompanied R, and the message, one can find out the collision for any other message M prime, so that the hash of M prime and this R prime generating the same hash value H. To verify a hash value H and accompany the R randomness, the verify function can be used. The verification of the hash value involves the public key only. Another building block for such fine-grained controlled blockchain rewriting is the ciphertext policy attribute-based encryption, CPABE, proposed by Bethencourt, Shanghai, and Waters in Auckland, 2007. In CPABE, attribute authority issues private keys to users according to each user's attributes. Then a data owner can encrypt their data using a decryption policy. The decryption policy is a logic expression of a user's attributes, connecting user's attributes with logic and or all. So example is this. The decryption policy specifies that this ciphertext can be decrypted by users with attributes director and ABC. Okay. So this user one, he or she has this attribute ABC and attribute director, so that user one can decrypt this ciphertext. But the other user here, their attributes do not satisfy this policy, so this user cannot decrypt this ciphertext. This CPABE has the advantage of simple key management. The crypto credential is issued to a user during system enrollment by attribute authority. After the users obtain their private keys, this attribute authority may stay offline. And users are in control. Data owners control who can decrypt their data using a decryption policy. A policy-based committing hash, PCH, can be constructed based on CHET and CPABE. The PCH setup runs the setup of CHET. So this public parameter generation is similar to the CHET key generation, generating a pair of secret key and the public key. And the key generation of a PCH is similar to the CPABE, generating a private key for each user whose attribute who has attribute set as. Okay. So this private key is assigned to a user with attribute S. Then the hashing a message M to access a policy P means that the CHET hash value is computed. If we compare the hash function in CHET and the hash function in PCH, you see that the output of this, you see that the policy is added into the input of the hash function. The policy specifies who can discover a collision, okay, for the committing hash function with ephemeral trapdoor. Then the output, you see that the ephemeral trapdoor in CHET is removed from the output of this PCH because the ephemeral trapdoor ETD is encrypted using the CPABE, using ciphertext policy attribute-based encryption under the access policy P. Collision finding is possible if the Dept algorithm in PCH has access to the secret key of CPABE. This secret key is assigned to a user with attribute set as, and the attribute as, the set as, satisfy the policy. Then this modifier with this secret key can find the condition for the hash value H, R. For any other message M prime, this modifier can find out the combinate randomness R prime so that they generate the same hash value H. The secret key of this modifier is used to decrypt the ephemeral trapdoor that is encrypted under this policy. If this user's attribute set as satisfy this policy. This figure illustrates the fine-grained blockchain rewriting at a high level. So transaction owner creates a mutable transaction with access policy. Then the transaction modifier with attribute-based credential can rewrite this mutable transaction if this modifier's attribute-based credential satisfies the policy associated with the mutable transaction. The transaction level blockchain rewriting is illustrated in this figure, where each block consists of the hash value of the previous block. Here, let's consider this block in yellow. It consists of the hash value of previous block. It also includes the set of transactions included in this block, the root hash of these transactions here, and the transactions are organized in a Merkle hash tree. And the root hash of these transactions is included in the current block. And the random number called nonce and the timestamp. In this figure, H is a standard hash function such as SHA-256. The Merkle hash tree is the same as the one used in the immutable blockchain, except that on each leaf node, for a rewritable transaction, the standard hash is computed on the communion hash value instead of on a transaction itself. So these leaf node in red are mutable. Okay. So the hash is computed on the communion hash value instead of on the transaction itself. The communion hash value here is computed on the public key, the underlying transaction here, and the policy that determines who can rewrite this transaction. So a modifier with a rewriting privilege can find the valid condition R prime for any revised transaction TX prime, such that the communion hash value R, communion hash value H remains unchanged. So a modifier can modify the underlying transaction to any other value TX prime without changing this communion hash value. If this modifier's rewriting credential satisfies the policy of this mutable transaction, then the modifier can find a collision for any new transaction TX prime. Accountability issue in the fine-grained blockchain rewriting is that the PCH-based redactable blockchain inherits the anonymity property of CPABE. multiple modifiers may share attributes and therefore rewriting privileges. Given a rewriting credential, no one, including the attribute authority, can identify its owner. So because of such anonymity, a malicious modifier may reveal their rewriting credential, even sell it publicly to gain profits without being identified. So this is an issue we need to address. A trivial solution to address this accountability issue is that in the credential generation phase, the attribute authority may encode the identity of each modifier into their rewriting credential, so that if a modifier reveals his or her rewriting credential, then one can retrieve their identity. Another way to identify the modifier is that the attribute authority keeps a record of mapping each rewriting credential to their owner's identity. So given a revealed credential, the attribute authority can identify the corresponding modifier. Here comes another issue. To avoid being caught, multiple malicious modifiers may build and distribute a black box device where their credentials and even the decryption algorithm are hidden inside. Given mutable transaction in the blockchain, any user can use this black box device to modify it if the attributes of any credential in the black box satisfy the policy associated with the mutable transaction. This trivial solution cannot be used to identify malicious modifiers from the black box because their rewriting credentials are not revealed but hidden inside the black box. To address this issue, Tian and others proposed a policy-based community hash with a black box accountability, PCHBA. PCHBA is built from the community hash with ephemeral trapdoor, ciphertext policy, attribute-based encryption, hierarchical identity-based encryption, and one-time signature. This solution enables any user, public user, to trace responsible modifiers from a black box. It also enables a central authority to link any modified object and its modifier. Let's say take a closer look at this PCHBA. In the key generation phase, each modifier's credential is generated from a set of attributes and a unique key index. The key index I is no less than 1, no greater than k, where k is upper bound from the index. Compared to the policy-based community hash, PCH, we add a key index I in the key generation phase. In the encryption phase, a message is encrypted based on the access policy, which is the same as before, but the encryption is enabled with additional condition, with additional message index. We call a hidden index. From the ciphertext, no one can derive what the hidden index is. This hidden index J is taken from the range of 1 to k, where k is the upper bound. So in the decryption phase, a modifier can decrypt a ciphertext if their attribute set satisfies the ciphertext policy. This is the same as before, but there is an additional condition for the modifier to decrypt the ciphertext. This additional condition is that the message index must be no greater than the key index in order to decrypt the ciphertext. In the when the transaction owner uploads a transaction into the blockchain, the transaction owner needs to encrypt an ephemeral trapdoor using the access policy and hidden index J to be 1. Here, using the smallest number for the message index. Then, when the modifier rewrite a mutable transaction, then because the transaction's message index is always equal to 1, therefore this condition will be satisfied automatically, because for any key index I, it is no less than this 1. So we don't need to worry about this condition. It is the same as before. If the modifier's attributes satisfy the access policy, then the modifier can rewrite that transaction. This solution enables a public user, any public user, to identify modifiers from a black box. So given a black box, any user can encrypt a message, any message, using access policy and the hidden index, starting from the upper bound K, then decrement it in the following trials. In each trial, the user sends the encrypted message to the black box and observe that whether it can be decrypted. So if the attributes of any credential included in the black box satisfy the user's policy and used in decryption, then the index I of that credential can be identified by this public user, because the once J, this J, the hidden message index is reduced to I, then this user's ciphertext can be decrypted by the black box. By observing that this message can be decrypted by the black box, the public user can derive the index of the credential hidden in the black box. Now we know how to identify contributing modifiers from a black box. A remaining issue is to identify modifiers from revised transactions. To address this issue, we need to answer the following questions. The first question is that should all mutable transactions be signed by their modifiers? Note that a modifier should sign not only on the ephemeral trapdoor, but also the chameleon hash randomness in order to prevent signature reuse attack. Another question is, should the signing key be bound to the rewriting credential, where the rewriting credential is used to decrypt ephemeral trapdoor of a chameleon hash in order to find a condition for blockchain rewriting, and the signing key is used to identify who has revised a mutable transaction. They can be the same, they can be different depending on application requirements. And the third question is what types of signatures should be chosen? We may consider Schnorr signature, ring signature, and identity-based signature. Once a malicious modifier is identified in a blockchain rewriting setting, it is natural to ask whether the attribute authority needs to revoke their rewriting privileges. A recent paper published in Isorics 2001 by Xu and others addressed this issue. Another paper also published by Xu and others in TRFS 2001 restricted the number of times each mutable transaction can be modified in blockchain. In Asia CCS 2021, Jia and others studied the supervision and the self-management of blockchain rewriting. Their proposed solution allows blockchain users to monitor the behavior of a centralized modifier called regulator in order to prevent the regulator from abusing its power. Finally, an ongoing effort is to replace a centralized attribute authority by a dynamic committee in a permissionless setting. So this is the end of my talk. I appreciate your time and welcome any questions.
Thank you very much, Dr. Lee. Any comments or any question?
If any participants are having any question, they can raise their hand or they can even write in the chat box.
Dr. Giri.
Hello.
Yes, yes.
Okay, nice presentation. Professor Lee.
So any comments from Dr. Giri or any question, any query? Yeah.
Oh, that is nice presentation.
Yeah. Okay. Thank you.
Thank you.
So, Dr. Lee, what is the application for this deductible blockchain? As you have mentioned, Accenture is using it. So, what are the
Yes.
applications?
Okay, that you know, since the arbitrary content have been injected into blockchain, right? They stay there forever. It is not appropriate. It is even against the law, like a GDPR. You know, this kind of data protection laws require that such content should be removed. But the current blockchain using the traditional hash function, you cannot remove such content. So that's why people are developing these blockchain rewriting technologies using Canadian hash functions. The Accenture adopts these adaptable blockchain used in a centralized setting. So a centralized modifier takes the responsibility of rewriting blockchain, but that may not be applicable in other settings, in decentralized settings. So that's why many other researchers are developing the decentralized blockchain rewriting and we need to consider, we need to address the issue that a modifier in the decentralized setting may modify blockchain maliciously, right? So if they remain anonymous, then it is not we cannot enforce the law, right? So we need to identify them in the accountable to make the writing accountable.
Okay. And what is the power issues? You know, the lot of power issues in blockchain, especially proof of concept, proof of stake is there. So, any comments on the power issues, power requirement?
Okay, here using this chameleon hash, the power issue is not a concern because the modifier, legitimate modifier, who has access to this ephemeral trapdoor and the private key of the chameleon hash function can find out the collision easily without consuming much power. It is not it's not similar to the traditional hash function. You have to try many random nonce in order to find out the qualified hash value. Here, if you have the private key and you can decrypt the ephemeral trapdoor, then you can easily find a condition. Then you can rewrite existent transaction without consuming much power. So blockchain rewriting is not a power. It's quite efficient, energy efficient.
Energy efficient.
Yeah.
Okay.
Is there any other question?
Yeah. Otherwise, yeah. Obijan is there. Obijan, any question? Obijan, Diganto. Okay. I think everyone understood all your deliberations. Thank you very much, sir. Thank you.
Thank you so much for inviting me to give this talk. I hope you, yeah,
Sure,
if you have more interest, you can contact me offline.
Yes.
Yes, sir.
Thank
If
you.
any question arises in anybody's mind,
Physically, we'll meet
yeah.
physically. With the hope, yeah. Thank you. Thank you very much.
Sure.
Thank you, sir. Thank you so much.
Thank you. Bye.
See you again. See you again.
Okay. Thank you.
So we are moving forward and entering to the technical session, paper presentation session. Shall we move forward, sir?
Yes, yes.